This video will walk you through regression in Excel, how to estimate the regressions, how to set the data up for the regression. Relatively straightforward because we're going to use the regression function that comes, the regression tool that comes in the analysis tool pack. So click the link, make sure you know how to get the analysis tool pack installed. We used it earlier for descriptive statistics, but it is absolutely necessary for this. There's a way to get around it and estimate the slopes without it, but it is quite a bit more tedious. So I highly recommend getting that analysis tool pack installed. So we'll work with housing data here. We're not going to work with the returns too much when we're thinking about regression. In a later section we will, but we want to work with a cross section of data when we get started with regression, and then later we may think about some time series regressions where the independent variable is just the time period. But for right now, we want to think about regressions where we have a set of independent variables and then use those to explain a dependent variable. So if you're looking at this data set, everything that we're going to work with is going to be quantitative right now. In another video, dummy variables, I'll think about this variable right here, area, where we can incorporate this type of variable into a regression. Right now we can't because this is not numeric. This is currently qualitative, and there's a step we need to take to convert this column into 0 and 1 dummy variables that we can include in a regression. So right now we're going to treat everything as continuous. In a later video, I'll show you how to generate the dummy variables and how to include those in a regression, and then how to interpret those coefficients. So the first thing we want to think about is which variable is the dependent variable, which variables are the independent variables. So there are a couple of dependent variables that make sense here. We might want to explain how long it takes the house to sell. We might want to explain the list price, or we might want to explain the sold price. So columns C, H, and I are the most logical dependent variables. It doesn't really make sense to try and predict the number of bedrooms or predict the number of bathrooms or predict the square footage. Those are variables that we will use to predict something else. And in this case, days on market, list price, and sold price would be the variables we want to explain. So for what we're going to do, we'll let sold price be the dependent variable. So this will be the dependent variable in everything we do. And bedrooms, full baths, partial baths, and square footage, those will be the independent variables. So I want to start off with a simple regression where we only have one independent variable, because we can estimate those using a scatter plot and a trend line. And it's nice if you only have one independent variable, you can plot the variable, the x and y variables at a trend line, you can visualize the regression. Once you have more than one independent variable, that technique doesn't, or that method isn't going to work. So the first thing we want to do is make a scatter plot. But keep in mind, when you make a scatter plot, Excel defaults the rightmost column to the vertical axis. So since sold price is the dependent variable, we want to make sure sold price is the rightmost column in our data set. And let's just pretend it wasn't. So what we can, I'm going to do this. So let's pretend this is what the data look like. Actually, let's do that. You don't have to do this, but let me just show you real quick. Let's say you want a scatter plot where sold price is the dependent variable, above ground square footage is the independent variable. If you try to click these two columns and insert a scatter plot, notice it puts above ground square footage on the vertical axis, and that's not what we want. We don't believe price predicts square footage. We believe it's the other way around. So what you have to do is whichever variable you want to be the dependent variable, right click, cut, come to the rightmost column, or actually the column to the right of your data set. We're going to do insert cut cells, and now sold price is the rightmost column. So I'm going to click on above ground square footage and sold price again, insert the scatter plot, and now we have sold price as the dependent variable on the vertical axis and square footage on the horizontal axis. And that's what we want for this regression. So the dependent variable is the sold price, the independent variable is the square footage. If we want to know the line that best fits this data, we can actually click on the chart. So just click anywhere up here, and you should see chart design show up at the top. So we want to click on chart design, add chart element, trend line, more trend line options. And we want to make sure we click the linear box. So we want a linear trend line. We also want to set the display equation on chart and the display of the R-square value on the chart. And notice it puts them in a very terrible place. But once you have your equation and R-square on the chart, you can move them to a place that's a little easier to see. And then if you need to, you can click in that box, go back to home, and then increase the font size so that it's a little bit easier to see. Okay. So what we have here is the equation of the line that we estimated and the R-square. So this, it's a strange format, but it will be strange every time in the same way. So you can get around it, or you can understand what it's doing. It always puts the slope term first and then the intercept last. So in this case, the intercept is negative 34,257. That doesn't make any sense when we have a continuous independent variable, and 0 does not show up in the data set. So notice we have this one observation way down here, but again, that's an outlier. We don't really care too much about that one. We don't think about the price of the house when square footage is 0 because that's an out of sample prediction. But this is what we care about right here. This is the slope coefficient. X is just a generic placeholder for the independent variable. So this is actually the slope coefficient for the square footage variable, which is 194.63, which says if we increase the square footage by 1 unit, the expected sales price will increase by $194. So we're looking at about $194 per square foot on average. So the slope of the line that we estimated right here, that dashed line or that dotted line, is the estimated regression line, and 194.63 is the slope of that line. This negative 34,256 is what we get when we trace that line all the way back to 0, and it intersects that axis at negative $34,257. But we don't care about that in this case. So let me show you how to replicate this with the regression tool so that you can see we get the exact same results. Oh, the R-square as well. So the R-square is 0.63. So we would interpret that as 63.65% of the variation in sold price is explained by the variable square footage. So square footage explains almost 64% of the variation in the sales price of a house. So if we want to do this with the regression, we're going to go to the Data tab, go over to Analysis Tools, click on Data Analysis, and click Regression. So hit OK. The Y range is going to be the dependent variable. So this is going to be the sold price. So I'm going to click in column I at the very top. And on a Mac, I'm going to do Command Shift down. That will go to the very bottom row of data. Once I click in the X range, this is going to be above ground square footage. And now that we know the ranges, we can just type it in. G1 colon G1472, because we know the range has to be the same. You can do the same thing, click in G1. So I could have done this this way. Click in G1, Command Shift down, and now I have the range filled in. Or you can just type it. It doesn't matter how you do that. You want to make sure you start in column 1 because we want to check this labels box, and that will give us the variable name in the leftmost column of our table. Output range, click the little radio button. I'm going to put it right here. Just don't put it somewhere you'll overwrite your data. So I'm just going to put it over here on the left, on the right side under the plot. We don't need to click anything else and hit OK. And now we can see our regression output. And if we scroll down just a little bit, I'm going to pull this so we can see them together. Excel does a couple weird things. It gives you 2 columns for confidence intervals, but they're identical, so you can ignore one of those. But notice right here, the R square was 0.6365. That's exactly what we get right here. If we were to round that to 4 decimal places, if we make that a number, 4 decimal places, we get the exact same R square. So the scatter plot and the regression plot give us the exact same R square. Our coefficient, notice the intercept, negative 34,256.7. Exact same thing we get up here, negative 34,257. Again, if we rounded that to no decimal places, we'd get the same number. And the coefficient for square footage, 194.63, 194.63. So we get the exact same information from the scatter plot or the regression using the regression function. So if all you care about are the coefficients, the slope, the intercept, and then the R square, you can use a scatter plot if you only have one independent variable. If you have more than one independent variable, the scatter plot method is not going to work for you. The nice thing about using the table, and while we use the regression function, is we also get the p-values for these coefficients. So we want to think about the coefficient. So what is the impact of increasing square footage by 1 unit on the average sales price? But we also want to think about whether or not that is statistically different from 0. So remember that in the hypothesis testing section, we assume square footage has no impact on the sales price. That's the null hypothesis. The alternative hypothesis is that the true coefficient, the true slope, is different from 0. The p-value here is 0. So we get a t-stat of 50, a p-value of 0. 0 is less than 0.05. So with 95% confidence, we would reject the null hypothesis that the true slope coefficient for square footage is 0. So in this case, since the p-value is so small, we will say that square footage is a statistically significant determinant of the sales price of a house. If we look at our confidence interval, we believe with 95% confidence the true value falls somewhere between $187 and $202 a square foot. So the point estimate that we got was $194. So if we increase above ground square footage by 1 unit, we expect the price to go up by $194 on average, but it could be somewhere between $187 to as high as $202. So that's our confidence interval. So everything you need from regression is in this table. You have the R square, you have the coefficients, you have the p-values, you have the confidence intervals. So you can do everything you need from this table. So the next thing I want to do is show you how to estimate multiple regression. So how to estimate a regression with more than one independent variable. So I'm going to go ahead and delete all of this because I'll delete this and let me move this stuff up here. I want to put the multiple regression down here below it so we can compare the two regressions. So the only thing you have to be careful about when you estimate regression with multiple independent variables, so we're going to go back to regression. In this first setup, we only had one independent variable, and that was above ground square footage. If you have multiple independent variables, they have to be in adjacent columns. So let's say you want bedrooms, full baths, and square footage as your independent variables. You want columns D, E, and G. You can't do that because you have column F in the middle. So if you want total bedrooms, full baths, and above ground square footage to be your independent variables, those 3 variables have to be in adjacent columns. So we want bedrooms, full baths, partial baths, and above ground square footage, and that works for us because they are in adjacent columns. So the quick way of getting these independent variables added to the X range is click on total bedrooms, or on the top left. I'm going to hold down Shift, scroll over to above ground square footage, Control or Command Shift down. On a PC, it would be Control Shift down. And notice our input X range is now D1 to G 1472, which is exactly what we want because our independent variables are in columns D through G, and they start in row 1 and go through G14 set or through 1472. So labels is still checked. Output range, let's just make sure we put this somewhere we're not overriding the original regression. So I'm going to add mine to K2, hit OK. And now we have regression output, and we have a coefficient for each variable, or we have each variable, the coefficients, and p-values for each variable as well. So that's it for estimating a regression. Relatively straightforward way to get the coefficients. Once you go beyond this type of regression, Excel is not really the best tool anymore. Something like R, Stata, SAS, even Python may be a better alternative if you want more advanced regression, but that's all you have to do to estimate regression. So let's take a look at this output. So notice the R square was 0.63, or basically 0.64, when we had one independent variable, and we're only at about 0.66 now. So I'm going to round, just to make life a little bit easier, I'm going to round everything to 2 decimal places here. Formatted as a number, 2 decimal places. So the R square increased a little bit. So when we added these independent variables, full baths, partial baths, and total bedrooms, so these are the new ones, we didn't explain much more variation. So remember that the R square is the amount of the variation in the dependent variable explained by the independent variables. So when we only have above ground square footage, we explain 64% of the variation. These 4 variables only explain 66% of the variation. And the reason those extra 4 variables are only explaining an additional, or a small amount of additional variation, is because these variables are going to be highly correlated with each other. Larger homes will have more bedrooms, more full baths, and more partial baths. So as we add variables to the regression, we're really not adding a lot of additional information to the regression. So it's okay to add them. We're not creating any problems by adding them. But don't be alarmed when you add variables that you think are really, really important and your R square doesn't increase by very much. It's because those variables are correlated with the coefficient that you, or with the variable that you already had in the regression. So if we look at our coefficients, we were getting sales prices increasing by about $194 per square foot when we only included square footage. And that coefficient is now all the way down to $156 a square foot. So what's happening, again, I'm going to format everything to 2 decimal places just to make it easier to see. You don't have to do this, it's just a little bit easier. I'm just going to go to 0 decimal places. We were getting about $195 a square foot when we only included square foot, and $156 per square foot when we include the other variables. And this is also an example of what happens when we omit important variables. So I think we could all agree that if our goal is to explain the sales price, this model would be more appropriate than this model with only square footage. So when we omit these other important variables, so this regression up here does not include these variables, that we get a number that we may not be able to trust. And that's because these variables right here, bedrooms, full baths, and partial baths, are highly correlated with the price, but they're also correlated with the square footage. So that's an example of an omitted variable bias type problem where omitting variables causes the other coefficients to change. So if we look at bedrooms here, this says an additional bedroom decreases the sales price by $16,478, holding the other variables constant. An additional bathroom increases the sales price by $67,985, holding the other variables constant. An additional partial bath increases the sales price by $23,116, holding the other variables constant. And an additional square footage increases the price by $156, holding the other independent variables constant. And we can look at our p-values over here. Again, I'm going to just go format all of this stuff as a number. All 0 to 2 decimal places, which says all 4 of those independent variables are highly statistically significant. That all of those variables are strong predictors, or more technically, are statistically significant determinants of the sales price of a house, holding the other variables constant. So notice we get an odd coefficient on total bedrooms. That may seem a little bit odd at first, but if you think about what we're holding constant, when we think about adding another bedroom, we're assuming the number of bathrooms doesn't change, the number of partial baths doesn't change, and the above ground square footage doesn't change. So if we keep everything about the house the same, the size of the house is fixed, and we add another bedroom, we might expect the price to go down because that additional bedroom is going to be very, very small. Maybe we took space out of the living room. Maybe we took space out of a different bedroom. Maybe we converted an office to a bedroom or something. So the coefficient looks a little bit odd, but you have to think about what else you're holding constant when you interpret that coefficient, which seems a little bit odd at first, but it is fairly sensible when you think about you're keeping the house the same size. Now, in the next video, we'll think about dummy variables, and we will actually convert bedrooms to something that is just create dummy variables for bedrooms, and we'll see that this odd result actually goes away. This is not the best way to model bedrooms because we're treating it as continuous, and we know bedrooms is very much discrete. So if we think about using the regression here, so we can think about changes. So the coefficients tell us how much we expect the sales price to change if we increase those by 1 unit. We can also use this to make predictions. So the way I like to do this, to make sure we're not making silly mistakes here, is below the table, hit equals, and then click the intercept column, and then drag this down so that we just replicate what we see here. If you can also just highlight this, copy it, paste it, get the same result. No problem there. But we want to do this so when we multiply coefficients by the values, we're keeping everything in the right order. Because I want to make sure I multiply the bedroom coefficient by number of bedrooms and full baths and so on. So just make sure they're in the same order. I don't care how you get it there, just put them in the right order. I want to put a value here. So when you're making a prediction, I'm just going to move this all down one. So when you're making a prediction, you always set the intercept to 1. So intercept is always set to 1. It's a constant. Let's set total bedrooms to 3, full baths to 2, and partial baths to 1, and above ground square footage to 1,500. So we want to use this regression to predict the sales price of a house with these characteristics. 3 bed, 2 bath, 1 partial bath, 1,500 square feet. So the way we want to do this, these are the coefficients, these are the values. So we need to multiply these coefficients by these values and then add it up. So we need the intercept times 1 plus the coefficient for bedrooms times 3 plus the coefficient for full baths times 2 plus the coefficient for partial bath times 1 plus the coefficient on above ground square footage times 1,500. So there is a function in Excel called SumProduct that will make this process a lot easier. So below the prediction cell here, you can call this whatever you want. You can call that whatever you want. But for prediction, I'm going to type SumProduct. And SumProduct will take 2 arrays of data, multiply them row-wise, and then add them up. So I'm going to highlight my coefficients for the first array, comma, highlight my values for the second array, close my parentheses, and hit enter. Just go ahead and round that to no decimal places to make life easier. Let's just go ahead and format it as $1. Because our dependent variables in dollars, our prediction will also be in dollars. So using these values right here, our best guess at the sales price of a house with these characteristics is $288,636. So some homes with those characteristics will sell for more. Some homes with those characteristics will sell for less. but on average, we expect the price to be somewhere around $288,636. So that's how we can use this regression output to make predictions. Well, let's say the house is 2,000 square feet. Well, change that to 2,000. There's your updated prediction for a house with these characteristics right here, but is now 2,000 square feet instead of 1,500 square feet. And to show you what these coefficients are actually measuring, so that they are measuring changes in the sales price of a house, we can do this. So let's go back to 1,500 right here. So we got 288,636. I'm going to copy that, and I'm just going to paste that value right here. So that's going to be my first prediction. Again, you don't have to do this. This is just to show you how exactly what these coefficients are doing. I want to change the total bedrooms to 4. So now I'm going to make the same prediction, but I'm increasing the number of bedrooms by 1. So this is my new prediction. Actually, let's not do that since it has a strange coefficient. I'm going to change the number of partial baths to 0. So I want to look at this house with no partial baths. Here's my new prediction. I'm going to take this one. Actually, I'm not going to copy it. And I want to take the difference in these two. So if we look at the prediction with a partial bath minus the prediction without a partial bath, we get $23,116. And notice that's exactly equal to the coefficient on partial bath. So this helps you see that all these coefficients measure are changes in the expected sales price when we increase the value of that variable by 1 unit, holding the other independent variables constant. So if I ask you to make 2 predictions and I only change the value of one variable by 1 unit, just look at the coefficient, because these coefficients tell you how much you expect the price to change on average when you increase that variable by 1 unit. So we can use the regression to make predictions. We can look at changes, predicting changes in the dependent variable. All of that is coming directly from these regression coefficients. So the next video, we'll think about dummy variables, how to generate the dummy variables, and how to interpret the output, the coefficients on dummy variables, and show you how they actually cause intercepts to shift.